So now you know how to run hypothesis tests using p-values, but you can also run hypothesis tests using confidence intervals, and that's what we're going to get to in a second. But before we do that, I want to talk a little bit about how we can use the z-score to run the same hypothesis test as that we use for the p-value. Remember that in running a hypothesis test using a p-value, we compared our p-value to the alpha level. And we could do this for either a one-sided test, where the alternative hypothesis either said it was greater than or less than, or a two-sided alternative hypothesis where the not equals sign was in our alternative hypothesis. We can use our calculators or we can use our z-tables to find that probability and compare it to some predetermined alpha level. We can also do this same test using our z-score. So instead of going all the way and calculating a p-value, we can stop and use the z-score, but what we need to do for that is to find a critical z. And for the critical z, it's going to depend on whether or not it's a one-sided or a two-sided test. And I will show you those critical z values in a second. But you want to think of that z-score as the amount of evidence that you have. So the more evidence that you have, the more likely it is that you can reject that null hypothesis. So it's the opposite of the p-values criteria. A larger z-score greater than some critical z means you reject the null hypothesis. That's the opposite of having a, if your p-value is really small, you would reject the null hypothesis. Alternatively, if the z-score is really small, you fail to reject, whereas that's going to make a really large p-value and you would still fail to reject. So regardless of which one you use, a z-score or a p-value, you're going to reach the exact same conclusion. Now here I've provided for you some traditional critical values that we see commonly, and they're associated with directly our specified alpha level. So you can see that the smaller our alpha level, the more evidence we're requiring, the higher our critical z value is going to be. There are two different types of critical z's based on how you specify that alternative hypothesis. If the alternative hypothesis is directional, then it's a one-sided test, and these are the z-scores you should be using. Whereas if it's not directional, it's just not equals, that's a two-sided test, and you should be using these critical values. You should see that some of these are familiar. So 1.96 is similar to that 95% region, and that's associated with this alpha level of 5%. And that's why these two numbers are directly linked, is because these critical z's are in fact coming from that normal model. The book reviews in more detail how these are generated, but I'm just going to provide for you here some of the more traditional values that we use based on the more commonly used alpha levels. So that's why there's a similar relationship between the z-scores and the p-values, because there's a one-to-one relationship between these critical z's and alpha level. And so you're going to always reject the null hypothesis for a p-value if you reject the null hypothesis for a given z-score. Again, I just want to point out that the signs on these are in opposite directions. So if you have a large z-score, then you're going to have a really small p-value. So those are two ways of running a hypothesis test. The last way is using a confidence interval, and this is mostly used for two-sided tests because with confidence intervals you create two tails. You create a tail above the interval and a tail below the interval, and that's why it's appropriate for two-sided tests. Confidence intervals and the hypothesis tests using a p-value have similar calculations, and we make similar assumptions, so that of randomization and independence. And so you would want to make sure that those assumptions are not violated to make sure that you are constructing a meaningful confidence interval. Once you've constructed the confidence interval, what we're going to do is determine whether or not a hypothesized value falls in that confidence interval. Remember that our confidence interval is how likely we think the true proportion falls in that range. And so if the hypothesized value falls in the range, then it may in fact be the true proportion. So we would fail to reject the null hypothesis. But if the hypothesized value falls outside of the confidence interval, then we're going to reject the null hypothesis. So this rule for determining rejection or failing to reject is common across all of the different parameters we're going to look at. So again, you're going to want to write this decision criteria down so you can quickly access it later. Now I'm going to go over a problem in just a second, but before I do that, I want to show you how the confidence interval is constructed. Now it's constructed similar to how we discussed before, where our main parameter from our sample is going to be our center point, and then we're going to reach up and down some margin of error. The main distinction here between the confidence interval and the hypothesis test is that we're now using a standard error, whereas in the hypothesis test for a p-value, we used a standard deviation and we utilized the hypothesized value to generate that standard deviation. Here we're using a standard error and we're using the sample proportion instead of the hypothesized value. So we're using our sample to generate an idea of what the variation might look like. So that's the biggest distinction between these two types of tests. For the intervals, you're going to use the sample proportion, and for the hypothesized test using a p-value, you're going to use the hypothesized proportion. The last thing we need to determine then is this critical z. This critical z is the same as the two-tailed tests that I just showed you, and it's the same as the confidence intervals that I showed you last week. But here are some more commonly used ones. Remember, there's a one-to-one relationship between the alpha significance level and the confidence interval. You can see that as your alpha decreases, your confidence can increase. And it does so because the z-score, or the critical z, is increasing. So again, we have a one-to-one relationship between the alpha, the confidence level, and the critical z. I want you to take a second and write these critical z's down. So again, you have them for easy reference on your homeworks and your exams. Make sure that they're easily accessible so you can do them quickly. So let's quickly go over an example so you can see how this confidence interval is utilized. In this problem, a magazine reported the results from a telephone poll or a telephone survey, and they were examining how men measured their idea of success. So maybe you measure success through work, maybe you measure success through your grades, maybe you measure it through how much money you're making or your family relationships. In this survey, they surveyed 1,085 men, and only 28 of them said they measure their success through work. So suppose we want to see if this fraction of men has actually fallen below 5%. So 5% is our hypothesized value, and our sample is going to be the proportion of men that we surveyed. So our sample proportion is actually 2.5%. And you can see that that is in fact lower than 5%. But we want to know, is this statistically different than that 5% mark? So our null hypothesis is that the true proportion of men who measure success from work as 5%. And the alternative is that it's just something different. So P here is the proportion of men who measure success through work. we're going to construct a confidence interval using our sample and then test to see whether or not this hypothesized value falls in that confidence interval. The way we calculate our confidence interval is by reaching up and down some margin of error. So here we've subtracted off a margin of error, here we've added a margin of error. This first number, 3.29, that's our critical z. And if you look at your notes of the critical z's, this is associated with a confidence level of 99.9%. So that's where this number comes from. The second term then, the square root term, comes from our sample proportion. So you can see that the sample proportion is in here, times 1 minus that proportion. So that's where I get this 0.9742 number, is it's just 1 minus 0.0258. Then we divide by the sample size because we want to take into consideration how many people we're polling. And so this standard error captures the variation in what we think our samples would be. And so that's going to give us a confidence interval from 1% to 4.16%. And again, this is a confidence interval of 99.9%. So we can interpret the confidence interval in the following way. We are 99.9% confident that the true proportion of men who measure success through works is somewhere between 1% and 4.16%. Now, that's where we think the true proportion falls. We don't know what the true proportion is, but it's definitely lower than 5% because we're really certain that it falls in this interval somewhere. And 5 is outside of the interval. It's in fact greater than the interval. And so we can make a statement that says which direction we think the true proportion actually is. So we not only reject that null hypothesis that it's 5%, but we can also say we have evidence that the true fraction of men who measure success through work is less than 5%. And so we started out with a two-tailed test, but we end up with a conclusion that's one-tailed because we rejected the null hypothesis and our proposed value was in the upper tail. So again, the conclusion is this: 5% is not in the interval, so there is strong evidence that fewer than 5% of men use work as their measure of success. That's the same interpretation that I just provided to you. So that's how you use a confidence interval to run a hypothesis test. Again, the main difference is in this standard error. And in the standard error, we use the sample proportion, whereas with the p-value, we use the hypothesized proportion to generate that standard deviation. That's the main distinction, and why occasionally you'll get different responses or different conclusions if you use a confidence level versus a p-value or z-test. Now, there are instances in which statistical tests are incorrect, that is, they make errors, and we can actually measure what those errors are. In the next video, I'm going to go over what those two different types of errors are and how we can measure them.